bottom all the time? I hope not.
You can, yeah, minimize the tab.
So here we go.
Wait, if I were to buy a bass guitar, which brand would you recommend me?
Well, it's being recorded. If you're gonna buy a bass guitar, what brand? Well, first it depends. Are you gonna stick with it? So I wouldn't bother getting something high end until you knew that it was something that you wanted to do. And I'd also recommend that you get into a band immediately, because you just have to say bass guitar. I bought a bass, and someone said you're in the band, because bassists are hard to find, and a good bassist is really hard to find. But I would just buy something used and something cheap, and probably have somebody that knew what they were doing to come along with me to make sure that the action was like halfway decent, so that you could actually fret it. And maybe it would, basses are a little bit easier to stay in tune than guitars. But staying in tune is one of the most challenging things for most new guitarists. And pressing on the strings and so. But anyway, we talk about this later. All right, so we have review session thrown off the rails right from the beginning. Good job. Review session for exam 3. We said already, rigid body motion. So if you want to break down the things, make it simple. Angular kinematics. That was what, class like 13, I think. Velocity analysis. And we know that we could do that in 2 separate ways. Well, actually 3 separate ways, 4 separate ways. I'm increasing them all the time, right? We could use vector math. We could use the 3 diagram method. We could use vector triangles, or we could use ICR, right? Various ways. And then we had the acceleration analysis, where we could use the vector math or the 3 diagram method. I don't really like using the triangles, which are actually quadrilaterals for acceleration, so we're not going to do that. There's the section on the equation sheet that we're using, where we have these equations that we're taking from. And getting used to the equation sheet, because it's your lifeline, it's a good idea. We, at least in my class, did not cover this portion down here, the relative motion on a body. I most closely associate that with Coriolis acceleration. Sometimes I'll refer to that as the Coriolis acceleration. That would have been class 17. One of the sections got rid of it because of a snow day. I got rid of it in my 1245 class because I wanted to align them. I think Dr. Orlup is covering that.
Yeah, we covered that.
Okay. It's just a little added complication, and most of the time the problems actually have to be kind of simplified just to be able to be doable. I saw one student came by with some of those problems in there. So there's a bunch of old exam questions from the Coast Guard Academy. I could run through any of these. I could run through a homework problem. We could run through problems. You could just say, hey, I'd like to see another problem of a certain type, and I could work through those. So it's up to you. Here's extra problems that I have on hand from Bedford and Fowler and from Beer Johnson. I can run any of these, strike you as, hey, I'd like to see that done. And I may or may not say, oh yeah, I'd like to do that.
On the exam, will you require us to do one problem like vector math and one problem 3 diagram, or are we be able to choose which way to do it?
I hadn't decided yet. It's a good question. I haven't made up my mind. I probably will ask one question with vector math, yes. And then the rest, I might just leave it up to you. Chances are there's going to be 3 questions. I haven't written it yet. Most of the time, 3 is about, I time the thing out, and then I say, well, I really want to ask 4, but just the amount of time that it takes me to do the thing, I usually multiply it by 2, sometimes 2.5, and then estimate for the best estimate.
For the problems, do you think you could do them in multiple different ways, like the same problem? You remember how we did that with the in-class problem?
Yep.
Could we do that here as well?
I will do my best, yes. I don't have them all written out that way, so.
Okay.
And I didn't bring my handy calculator, now I have to use my phone again. And that's fast.
Photomath.
So, was that
Photomath.
photomath?
Yeah.
Don't know what that is.
Exactly.
All right, so what would you like? Do I have a request for a problem type?
3 linkage problem. That deals with velocity analysis.
A I think you mean a 4-bar, but that's okay. Yeah, there are 3 linkages, but they're technically called a 4-bar. Like this thing is a 4-bar right there, even though there's 3 linkages. It's just silly. That's what they call them. So we have that problem. Here's a 4-bar right here. This one right here is actually a really long problem. I would never ask this problem by here. It's actually not too bad. This is actually just for velocity. It's if you have to do an acceleration, it becomes too long of a problem. Do you want to see this one?
Also, one question. Is there gonna be a problem related to time that will be coming on the test?
I don't know. I don't know what you mean, but I don't think so.
I have a question about the 4-bar. Isn't technically the ground the 4th bar?
Yes, the ground's the 4th bar.
Why on the one that was like mounted to the ground and the wall, why isn't that considered a 5-bar?
Well, it's because what you would do is
That one right there.
you would just draw a straight line between that thing and that thing behind there and call that the bar.
Gotcha.
Because there's just actually how many move right to the thing. Right. There is such a thing as a 5-bar. But you don't need. I don't need to teach you mechanisms today right here. But that's an extra degree of freedom which is solved because they put gears on 2 of the legs that force them to work together to make things. Do you want to do this one or do you want to do the other 4-bar? That one.
Which one's more difficult?
This one's a little bit more difficult right here. It's all about the angles right there at C. It's if you could keep something straight up and down or horizontal, it greatly simplifies the problems. That's when you get the stinking angles right in there. And this one's only a velocity problem, but we can make it into an acceleration problem. Did I do that here in my wonderful stuff? Class 12.5. What the hell does that mean? Right here. So, in terms of methods, let's just do the velocity thing and see how that goes. All right, so in terms of methods, we can start out and do vector math first. And this is my desire to, this one is lower than that one. So this might require, did they give us angles? They didn't give us angles, those bastards. How come they didn't give us angles? So this is 200, 350, and here's 300 and 350, and then they told us this is 12 radians per second. So for vector math, I think the best way to start out is to start writing out some of the equations that we're going to need. That's kind of obvious. So what did they label this? A, B, C, and D. So start out with velocity of B. It's going to be equal to the velocity of A plus velocity of B with respect to A, which we know is going to be omega AB K crossed with R B with respect to A. Velocity of A is 0 in this case, and omega is, we know it's negative 12, and I'll keep going this way, okay, and then R is simply going to be 200J. So that's B with respect to A, so it's going upwards from A, looking at B. Take the negative 12, multiply it by the 200, and we have the K crossed with J. I, J, whoops, I did that wrong? Yeah, no, I'm good. Yeah. I, J, K. We're going to cross K into J, and that makes a negative I. Just memorize it, I guess. So you have 12 times 200 is going to be 2,400. Should be able to do that in my head, but I can't because the negatives cancel each other out. But that makes sense, right? Because the velocity is going to go that way in the positive direction. So millimeters per second. We have a choice. We could either do BC or we could jump to CD. We're going to have to do that anyway, so we might as well. Let's go to CD first right here. So this was AB, there's CD. And for CD, we don't know omega CD. That's one of the two unknowns that we're looking for. In fact, in the problem, we're looking to find the angular velocities, right? Determine the angular velocities of B, C, and CD. So we write out the velocity of C. It's going to be equal to the velocity of D plus omega CD crossed with R C with respect to D. And this is a point where we have to be a little careful. I have to make sure that we're going to get the signs correct, that we are at D looking at C. Of course, D is fixed, so it's 0. So the velocity of C is going to be equal to, could write out the 0, but we don't need to. And K crossed with, and then here we go. Kind of nice that they didn't give us the angle because we don't have to do sine and cosine with this right here. We could just say that the x direction is going to be negative 350 I, right? It's going to the left and it's going up 350, right? So you can tell that's 45 degrees. I could do that in my head. 45 down there. 350 J. So VC is going to be omega CD times negative 350 K crossed with I plus omega CD 350. Oh, that's terrible. 350 K crossed with J. From here, we can see that K crossed with I goes up positive J. And this, just like before, is a negative I. So we could write out that the velocity of C is going to be, they're both going to be negative. So they're going to be negative 350 I plus a negative 350, omega CD I plus a negative 350 omega CD J. And now we can go back to BC and say, well, we're going to find, once again, it's better to write velocity of C, because we're going to use that right here. So we have the velocity of C. It's going to be equal to the velocity of B plus omega BC K crossed with R C with respect to B. C with respect to B. So velocity of C is gonna be equal velocity of B, so that's 2,400 I plus omega BC K crossed with, and we're looking at C from B, so we're gonna go to the right, positive 300 I plus, and we're gonna go up 350 minus 200, so that's 150 J. And 2,400 I plus omega BC times 300 K crossed with I. We know that's J. Plus omega BC 150 K crossed with J. We know that's negative I. So we're almost there. So for this, we're gonna get, I'll put it together for I, 2,400 minus 150 omega BC I plus 300 omega BC J. Now we set these two things equal to each other. So I would say the most convenient way to do it is to take, let's just take J's first. And we'd say negative 350 omega CD is going to be equal to 300 omega BC. Is anybody, but you guys are keeping track of whether I'm making mistakes, right? Because I haven't looked at my page. I don't have this one written out as in this way. We'll see what happens. So I don't know, make it easier here. We go omega CD, doesn't matter which one we do. It's going to be equal to negative 350, no, 300 divided by 350, right? I do that wrong. I can't do this shit in my head. I gotta be sitting at my desk, staring at the piece of it. So that's a negative 0.08571 omega BC. We could plug that back into the I. I can't make an I right now. There you go. My brain's not working. Got negative 350 times negative 0.8571 omega BC. I just shoved it back into here, right here, right? I put that omega CD I just got right back into there. And that's going to equal this mess over here. 2,400 minus 150 omega BC. All right, so I guess I'm going to multiply this by 350. It should come out to 300, right? Is that true? No. I think I just said something and then typed something differently in my calculator. 350 times that. Yes, comes out to 300. Should have been 300. And it's a positive 300. And then this is going to jump over to that side right there. So we're going to add 150 to that. I can do that. It's 450. So we're going to divide 2,400, and we get 5.33333. Yeah, that was one of the answers. Good. Okay. So omega BC is 5 point, and it's positive, 5.333 radians per second. And then we can get omega CD is simply going to be negative 0.8571 times that. So that's negative 4.571 radians per second, if I did it right. Yay! You're excited? You're excited? We got the right answer. Did you ever doubt it? You did. You didn't.
No,
You didn't believe in me.
What, no, I wanted to just ask something real quick, so.
Okay.
When it comes to the vector math, with the angular velocity, do you always assume that k hat is positive?
Yeah. If you don't know it, just assume it's positive.
Okay.
It's my opinion. I mean, you can go crazy and assume it's negative. And then if you get a negative answer, boom, that means you were assumed wrong. But if you get a positive answer, you're assumed right. I don't know. But 3 diagram method. I don't know, we need to move the camera. We could leave the stuff up there. I personally prefer the 3 diagram method. But so we just start out with the first link. We know it's going this way right here. And we know that omega, so we know that this V B is just going to be equal to omega AB times LAB. So 12, it says it right there, 12. 12 times 200, get the same thing, should be 2,400, right? Yeah. And then, yeah, this becomes the hard part in the 3 diagram method often here. So I'm going to skip over to this guy right here. And we don't really know which direction he's going, so we can assume he's going counterclockwise right here. And kind of put this in here. Here's the velocity of C right there, and here's a omega CD. And in this, I kind of do want to get the angles. So even though I didn't draw it this way, this one's 45 degrees, which makes it kind of easy, right? To try to figure out where that angle is. But still, I like to try to get the right ones, even when it's 45 degrees, to try to get the thing. So we can make, that's 45 degrees right in here. So that has to be 45 degrees right there. But again, it didn't matter because it was 45 degrees. And we know that that, by the way, is equal to omega CD times LCD. Then we can go back up and do the 3 diagrams of this guy. And leave enough room for myself. I guess I'm done. Make a bunch of hot dogs. Hot dog would be good. I go for dog. Could we call Uber Eats or somebody to just order food while we're doing this? We should probably get pizza next time.
For the final?
For the final, we should get pizza for the review session.
Cooking hot dogs in a hot dog cart in front of the room.
That'd be great. I like that idea.
Nathan's hot
We
dogs.
should make that happen. Make it happen. All right. So we've been using this color too much. Maybe let's go. I don't know. Green. This green's better. I like it. I don't know. Hard to make a decision. So let's put on to the velocities that we have right here. VB. We know this one in its entirety. All we know about this one is, we probably should actually guess the other direction because we're pretty sure it's going to be the other direction. All we really know for sure is that it's going to be at 45 degrees. And that's going to be, for this, it's actually going to be up above. So I'm going to make that look correct right there. We were never given this angle. We'll see it in a second. Because we know everything about VB, we'll use that as the reference. And that means we're going to block it right there. Well, now, at this point, I should get the angle of this piece right here, so let's see. I'm going to call this beta, and beta is going to be, what, the inverse tan of 150 divided by 300, which is 0.5 to me, yeah, of course. So that's 26, that's not one I memorized, 26.57, sure. So 26.57 right here. And since we've already used positive here, let's use positive here as well. We'll get red. I like to make accelerations red most of the time, but this time we're gonna mix it up, just go crazy. This is BC, not CD. Crazy, just crazy talk. All right, so it'll be in that way, and I've decided to assume positive. So your VC here is, and that so that angle right there is pretty obvious. That's going to be my beta. So everything is really, basically it's doing the same thing, right, as over here, right? As our scheme is we found a velocity using, for one link, and we know it had to be the same velocity as this other link, so we're going to do the same thing right here. We have this velocity in that direction, and we have this in this direction, right? So I'm going to go ahead and draw this guy right on there. And even though this is a terrible drawing of the thing, that is 45 degrees. I know, it's stupid, but, well, no, maybe, yeah, it's supposed to be 45 degrees, right? That's the same, this is the same guy as that. I just have not oriented this thing very well. It's just kind of screwed up because of that. I don't know. If I had a ruler, I'm not making excuses, but it sounds like I am. So this is the velocity of C. Oh, by the way, this is the velocity of C with respect to B. Woo! Sorry. That's velocity of C with respect to B, which we know to be omega BC times LBC. So write it out as an equation here. It's only slightly different. The velocity of C is equal to the velocity of B plus the velocity of C with respect to B. So I don't think there's there's no simplifying thing here, so it doesn't really have any advantageous thing to be able to do one or the other first. Sometimes if something's aligned with the horizontal or in the vertical, there's an easier way an easy one to do first. This is not the case here. So I'm going to keep everything as it's drawn on here for the VC, and so we're going to take omega CD, and this is negative, it's showing it as negative, negative omega CD LCD, and that's going to be the sine of 45 degrees. And that's going to equal my VB 2400. And then over here, as drawn, this is also negative. And it's going to be omega BC times, by the way, I never found out what these lengths are, did I? Unfortunately. So LBC, I'll just say it's the 150 squared and 300 squared. Square root. I think I did that right. Now I'm not sure. So sure. 335.4. And this would be sort of kind of unnecessary. I could have probably, since we're gonna, whoops, that's the wrong one. Sorry. Need to go LCD as well. And that's just 350 times square root of 2, right? And we're gonna say, yeah, that's right, Dr. Dale, sure.
Yeah, that's right, Dr. Dale, sure.
Thank you. Need to keep you around more. 494.97 is 494.9. So 495. I think that's right. Which is, of course, just going to come out to be 350. We could have just put 350 right there. But anyway, okay. So this is the one where I need LBC 335.4, which and then you're going to go the sine. Okay, so once again, it's going to be negative because it's going in that direction. It's going to be opposite from that angle. So it's going to go for the sine of 26.57. So we might want to go ahead and simplify this thing and go negative. Like I said it was going to be, so 45 cosine times, you have a 350 omega CD. It's going to be equal to 2,400, and then minus, and see, I think it's going to come out to 150, right? That if we take the sine of 26.57, multiply by that, yeah, 150, makes sense. And then in the y direction, we're also going to have a negative omega CD and the 495, and now the cosine of 45, and it's going to be equal to, got nothing here in that direction, and then this is going to be positive, so it's going to go omega BC times 335.4, whoops, that's ugly. 335.4 times the cosine of beta, which is 26.57. And that too should come out to negative 350 omega CD equals, and I'm guessing that's going to be 300. But are you really plugging into your calculator? I said, sure. Look at that, 300. We're damn close to it. BC. So we have two equations and two unknowns. We could do the same thing we did before, right? But isn't that the same thing where we have, here you go. Got that, right? That's same as my equation 2. And then I didn't actually write this one out, but I would have gotten the same thing. I'll get the same answer, won't I? Everybody agree? Do I have to do the math for the next thing? No. But let's do, oh, go ahead.
I just wanted to ask one thing. So when you are using trig, couldn't you have just used the I and J components, or do you have to use trig first?
No, I was just trying to simulate what would typically be done in a problem. But this problem was a little different because they didn't give us the lengths. They just, and I could have simplified it, but I thought perhaps students would not have, would not jump to that from looking at this. I wanted to make it similar to problems that other problems we've done. But I mean, I totally could have just skipped that thing, but I wanted just to make it look that way. And then the last thing we would want to do which is actually what's on my page when doing this, is to do it with using the ICR. So a 4-bar is especially easy to do ICRs with. I mean, it's easy, well, let me put it out. It's easy to identify what the ICR is from just a simple trick that you could memorize. But still, it can be challenging just to get the angles to work out. So you could figure out how long the ICR is going to be. In this case right here, I'll try to show in here. We have, all we have to do when we want to do an ICR with the 4-bar is just to extend the legs to see where they will meet. And boom. So that's going to be the ICR of this link right here. But we have a little bit of a hassle. So like a lot of times, just to cheat a little bit, to make my life a little easier, I like to break triangles up into smaller triangles, into right triangles if I can. If we have a bunch of weird angles, I mean weird, let's just say what's weird. One thing is nice is that this link is straight up and down. But actually finding this angle right here, which I call phi on mine. I'm just taking a look at what did I decide to do? I said that my ICR, okay, well, why? I'm looking at my page and I jumped and I said, somehow I knew that this was going to be, oh, I know why. Can I say? Are these guys in line with each other? Okay, I did not draw them in line with each other. That was part of my problem. As I was looking at this, stammering around, these guys are on the same plane. Okay. So, and I know this is 45 degrees. So I could find that length right there, even though I didn't draw it this way. This one right here should be 650, right? We're all in agreement? If that's 45, this thing must be 650. Even though it doesn't look it. It's gotta be, that's 45. So therefore, this leg right here is going to be 650 minus 200, right? Or 450. And this is, by the way, this is my ICR. So this is ICR, doesn't look like it. This is my RB with respect to ICR. So we know that the velocity of B is equal to 2,400. So, and going that way, so we can find omega BC. Omega BC is going to be equal to the velocity of B divided by R, B with respect to ICR, or 2,400 divided by 450. You can take my word for it. It's 5.333 radians per second. Now we want to find where this is. This is RC with respect to ICR. And we can already see that we're going to have a velocity of C that's going to go in that direction. What's the easiest way to do this one? you take it. How did I find it? Ooh, okay. Oh, I said what I did. I took square root of 2. Oh. So this entire length right here would be 650 times the square root of 2, right? That leg from here all the way down to here, because it's a 45 degree triangle. So the hypotenuse is just going to be the leg times the square root of 2. So we go R of C with respect to ICR is going to be square root of 2 times 650, but we're going to subtract out the length of one of the things. We already found that the length of this was 495, so that's why I'm writing 495 here. So we end up with 424.27 millimeters. So we could find the velocity of C is going to be omega BC times RC with respect to ICR, or 5.333,424.27. So that's going to be equal to 2,263 millimeters per second. So if you wanted omega CD, take that VC and divide it by the length of this. So the length of CD, yeah, and 2,263 divided by, what did I say, 495.0, and we get the 4.572, I'm calling it here, radians per second, but I might have, yeah, same minutes. So I got all three, we got 3 ways that we did it, and if we wanted vector triangles to complete everything, a little ugly. It's really this equation that you use for the vector triangles. I'm probably gonna get the angles all messed up. But we say that so VB, so they're moving that way, and we really ought to try to like pick out the correct directions for the thing. So VC is going that way. It's not going as it's drawn here. It's actually going up that way. And this thing is actually rotating it is going counterclockwise. So that is the direction, but it still should be, that should be 45 degrees right there, right? So that should be, VC should be coming up in that direction. So I feel like I'm going to screw this whole thing up. That's all right. I've screwed things up before. So, so that's going to be VB, VC with respect to B, and VC. And so that is going to be a 45 degree. And then this, if I had it correct, I think this is actually that angle beta right in there. So this is like 90 minus beta right in there. So by triangles, what we could do is, okay, well we can from that we can establish what this angle is going to be from 180 minus these. So we could use the law of sines to find the magnitudes of these other triangles, of these other legs. And from that you could do the rest of it. Does that make sense? I think I drew it correct. All right, that was a long one. I did it 3 ways though. 4 if you consider the triangle, but I didn't really do it. So we want to do another problem? Let's do another problem. I know that's long.
Is that ICR, like extending the legs, work for most 4-bar?
Yes, yes. If they're ever parallel, remember that means that it's just, moving, it's going to be in translation, pure translation. But I don't think this one could ever do that. But there are some that could be, if they're in a certain orientation, they could be in pure translation. So most of the time, I don't think I'll ask for a 4-bar for acceleration because it does take a while to do. And so if we're going to do an acceleration one, we should probably, like this one, see, does this one have, I know I did this one. Yeah, that one would take too long. Ooh, yeah. I filled up the entire page. My spare time. I probably screwed it up like 4 or 5 times. Oh yeah, I even have an angry face. Or an angry face next to it somewhere. So, not a good exam question. But if you want to torment me, you could ask for it. Let's see, is this one, how bad is this one? Let's see it. Where'd you go? It's not too bad. Can you see the ICR? This is a game you can play to test yourself if you're not. Actually, my scheme for trying to get you better at ICRs was to ask you, one of the problems and for that assignment, right, where you had 10 different ICRs in there. Kind of test yourself. You could just wipe your memory and then do it again, because I posted a solution to it, but cover that part up. Test yourself. Go through the whole all the problems in the book. Just ICR, just to make yourself do it. To go for speed and accuracy, all right? So how fast can I find the ICR onto things? Can you find it on this one? It's good to use your pencil and your paper. Sketch the thing out. And if you had a ruler, hey, I know that you do, or you did. Talk to you soon. Man, this boy ain't so great. Maybe it's the pens. Someplace in that stuff so fast. You can speak up anytime you want and say, hey, this is what I'd like to see. You're going too slow, doctor. Or you really should get a haircut. No, don't hurt my feelings. I'm not getting haircuts because they made me get haircuts at the Merchant Marine Academy. They even made me pay for haircuts when I was out at sea and wasn't even there to get haircuts. I don't know if I resent that more. That they made me buy football tickets for the football games I couldn't go see because I was out at sea. That's messed up. That's messed up. They say it's free, but then they charge me money for fees and things. All right, so let's off the hook for the ICR. This thing. See, I'm going to draw it in the right spot. Where's this thing? 200 millimeters again. I don't know if you noticed, I like to mix it up between inches, feet, meters, and millimeters for the problems. A little variety, keep things going, keep things fresh. I know you appreciate that kind of attention to detail. It keeps you up at night thinking about it. I hear you. I'm with you. What they say the angle was? 60 degrees on this board. And I didn't really, I guess it is not so bad. It's bigger than 45, right? 45 over there, yeah, sure. So, ICR. Well, this one's straight up and down. Whee! And then this one, we extend them up there. Here's your ICR. Is that where you picked it? Is that where you found it? Yeah, sure you did. No, I believe it. Okay, so we could find our velocity for this guy right here. Our velocity of, I'm guessing he's B, he's Q. What kind of maniac goes Q? Q. Here's P. Here's O. Crazy talk. VQ is omega OQ times LOQ. And I didn't actually see which direction it was going. Counterclockwise. So I was all excited about drawing in that direction. Counterclockwise. So omega OQ, just throwing me off the game here with the mixing things up like that. 2 times 200, 400 millimeters per second. All right, so give me a VQ up there. So that's guy right here, omega QP. Have a great weekend. It'll be right there. And so our dimension we want to try to get is this RQ with respect to ICR. We're going to have to get this here. Actually, we don't even need it. We could get it, but nobody is asking us for the velocity of this thing. But if they did, that's what we would need up there. So let's see. How did I do my geometry right here? I decided, okay, so I broke this up into, and decided to call this beta. Big fan of beta. It's going to be, did I play around with this? I said 180 minus, where did I find this? Oh, I did the law of sines. Okay, so law of sines, to be able to find what my beta is going to be, I said that if 400 divided by the sine of 60 is going to be equal to 200 over the sine of beta. So I was able to find my beta to be 25.66. And therefore, if we were to care, this angle right here, let's call this psi. Psi turns out to be 94.34, which is sort of a cautionary tale, because you're looking at that thing, you go, that's got to be 90 degrees, but it's just a little bit more than 90 degrees. Just kind of, sometimes you just get tricked into, these assumptions. Okay, so in order to do this, let me think. We are going to find these angles. did I do this? I said that, yeah, okay. So this is we could find this dimension right here now, right? Bless you. And this is we can make this side over here. We could find this side fairly easy by, sorry about this, let me think. I'm looking at my mess right here. And I said, where did I get 460.56? Oh, I did my law of sines again. By the way, there's a bunch of different ways we could possibly do this, but we want to find this dimension between here and here. I called it OP. So OP is really going to be, let's see, you can find, you use law of sines, I guess, to find it. So we could go the sine of 94.34 equal to, easier one to do is the 400 divided by the sine of 60. And I found that one to be, so OP was equal to 460.56. That's a lot of sig figs. And then from that, I can find him, which I didn't actually need, did I? Oh, okay. So because I don't need this one, I'll do this one instead. We could find RQ with respect to ICR by taking this and dividing it by the cosine, right? So if I take 460.56, divide by the cosine of 60 degrees, I get this entire length, and then I could subtract out 200. So for my ICR, it comes out to 721.1 millimeters. And then for my omega QP, it's going to be my velocity at Q divided by that RQ with respect to ICR, and that ends up being 400 divided by 721.1. And where'd you go, buddy? I think it's 0.5547 radians per second. And then all right, so that would, and then if we wanted to, we could find this, we could find that velocity, but this, I want to do the acceleration analysis, that's what they're asking for. So we proceed with, we could have done this before, but this was a constant velocity, so even though it's not going to have a tangential component, but it is going to have an acceleration at Q. It's going to be the omega OQ squared times L OQ. So, well, I guess I need to give myself some space. And we know that that's actually Q with respect to O in the normal direction. We have 2 squared times 400. So, is that going to be 1,600? No, it's going to be 8, no, right? Oh, times 200, that's what happened. I'm losing it. 800 millimeters per second squared. And so for link PQ. We do our 3 diagram method here. Equal plus, and put in what we know. One thing is we know this is going to be horizontal. Here we have this is going to be a little tough to draw. I'll go up a little bit. There you go. That's going to be nope, wrong, down. Sorry. So this is the acceleration of Q. And looking at these angles right here, this is 60 degrees, so that's 60 degrees. That's one of the most important parts to practice is trying to figure out those angles, to get them right, figure out where it lands. So since we know that acceleration, here's your V, AQ, there's AQ. We're going to put that right in there and then have acceleration here, and we're going to assume this PQ is in that direction, and so that makes this acceleration of P with respect to Q in the tangential direction that way. Acceleration of P with respect to Q in the normal direction is that way. And the really important part here is to get these angles right in there. So, this one's pretty easy. This is going to be that same beta that we got before, right? That's going to be this beta that we found. I'll write it as beta. And then, so that means this one right here has to be beta, right? We agree? You guys don't give a shit. No, I'm just joking. You guys are just like so nervous about this exam. You're just not ready for fun, right? You're like, no, right? It's so tedious, it's so evil. It's not that bad, really. Just kind of get it like, okay, yeah, I can do it. Yeah, it's not that bad, sure. What you want to do is you want to find one of your classmates that's struggling with it and teach it to them. And then they're going to be like, wow, you're amazing, and you're going to feel good about yourself. And then that's one way to try it, right? You can try it. It'll work. So anyway, what the equation that we're writing for this thing is we're trying to find the acceleration of P. So we're using an acceleration of Q that we do know, plus the acceleration of P with respect to Q, tangential, plus the acceleration of P with respect to Q, tangential, normal. It's not normal. So we're writing the equation for this spot. So first thing that should jump out at us is we have a strategy. We could go in the y direction because it's 0. All right, that's nice. So we do the y direction part of this. And we could actually be done with it, like just after that, because all they asked for was the angular acceleration of the thing. We don't even have to do the x direction. They didn't ask for the acceleration of P. So we go 0 right here. And then for right here, remember this was 60 degrees. And it's negative. We're going to go negative 800 times the sine of 60 degrees. And then this one is going to be, remember that this is going to be alpha PQ, right? PQ times L PQ. So that's going to be, and as it's drawn, we're talking, it's positive. So plus alpha PQ times the length of the thing, which is 400, times the cosine of 25.66. And now we want this guy right here, which we never wrote out because he was omega PQ squared times L PQ. And he too is going positive, so right in there. So he's going to be plus omega PQ, which we found to be 0.5547. I don't know if I'm missing this camera. He's probably in there.
Where did you get 800 from?
This guy. And that's also times this 400 length. But now we're going to go the sine of that beta. 25.66. If we did all this right, alpha PQ we can solve for. It's probably going to be positive. We get 1.773. 4 radians per second squared. Hey, that's the answer. Wee! Or I could have just been, it could be a hoax. And I don't even have the, because I printed this out and the number fell off this thing. But if you wanted to know like which direction it was accelerating, can you tell which direction it's going to, P would be accelerating? Going to the left?
Yeah.
I think so too. Probably just by magnitudes. Does that mean it's moving to the left? That's the tricky part. Well, you can already tell that its velocity is going to the left. So yeah, it is moving that direction. But it doesn't have to. The acceleration doesn't have to be in the same direction as the motion because things could be slowing down. It's hard, you gotta always remember that. It's just the change in velocity. It's not the direction of its motion. Can be, doesn't have to be. All right, what kind of other problems we want to do? I don't really want to do this one by vector math, but we could attempt to do it by vector math if you wanted to. If you wanted to. Not a lot of fun. Do you want to do it by vector math? No, you don't care. You don't. Do you care? Do you have any? What kind of pizza do you like? Like what do you like? What do you want? What would make you happy? Would you like to see me dance? You don't need nobody to see me dance. My wife won't even dance with me anymore. It's embarrassing. But it's a lot of fun to embarrass her. She has a particularly fun person to annoy. Let's do. See if any strike your fancy. Is this a velocity one? That's a velocity one. Here's a velocity one. Pistons. This is an acceleration one. Yeah, it's an acceleration one. You can't even read that. Look how small that writing is right there. This is actually a straight line mechanism. Ooh, exciting. Straight line mechanism. Richard Roberts. This is one of Robert's things. Robert made a straight line mechanism. It's exciting. Close approximation.
Good weekend.
See you. Have a great weekend. Beer Jensen. Oh, look at me, Lamey. I copied the solution manual for this one. Ooh, that's a long problem. Ooh. Oh, we don't want to do that. We don't want to do that one.
Can we do the one that was like before that one?
This one?
Yeah,
Okay. Do you want to use vector math for it?
sure.
Have a good weekend.
Actually, that's not too bad. The solution manual one doesn't make it look too bad. So, knowing that the angular velocity of rod dE is constant, ooh, that makes life a little easier. Oh, something of note for as a practical matter for exams. Generally, what I'll do, even though it is true for acceleration analysis, you have to do a velocity analysis first. Because I will be testing you, measuring you separately, for the acceleration problems, I will give you what the angular velocities are of all the pieces. Does that make sense?
Mhm.
Yeah. So, makes it a little less tedious. Well, at least I don't have to do that. All right, so still, even though we're going to do this vector math thing. Oh, by the way, the one down at the bottom. So I can either do this at the top or this at the bottom. What do you want to do? One of the bottom's more complicated. Just slightly more complicated. Do I have that one printed out? I don't have that one printed out, so never mind. Let's not do it. So this one actually has an angular velocity and an angular acceleration. That one doesn't, so prefer that one. Let's draw out the problem and then turn the projector off. So and this is 6 inches, 24 inches, 10 inches, and you are 8 inches. And it's length DE is going clockwise at 20 radians per second. I didn't put the letters on here. ED, that spells Ed. Really don't like the name Ed. Oh, I'm sorry if you're named Ed. I didn't like that. That'd be rude. My parents named me Edward and didn't tell me. They just called me Teddy. It wasn't until I got into like, what grade is it? It's probably first grade. I don't know if the kindergarten teacher probably called me that. But the first grade teacher insisted on calling me Edward all the time. And all the kids knew that I was annoyed by it, so they all called Edward, Edward. Kids are awful. That's a weird thing to have written. They wrote it though. Okay. We'll start off with the thing that we know. We have omega dE is equal to negative 20. K. And our R, D with respect to E is going to be 6, negative 6, I. Inches, if you want to say that. So we can find our velocity at D is going to be velocity of E plus omega dE K crossed with R D with respect to E. So 0 plus negative 20 and then times negative 6 and K crossed with I, which is J. So that ends up coming to, I literally can't remember what 6 times 20 is. That's how, like, maybe a little bit out of it I am. Yeah, 120. And then we could skip up to this one and go, the velocity of B is equal to the velocity of A plus omega AB, not known yet, times K crossed with R B with respect to A. So A is 0, velocity B is going to be equal to omega AB, bless you. Let's see, so it's going to be B with respect to A. So you're looking downwards, so it's going to be a negative 8. And we're going to have K crossed with J, which is negative I. So we kind of knew there was going to be the I direction, right? Either to the left or to the right. We're not quite 100% sure. But we know that it's going to be 8 times omega AB I. Still unsure whether that's positive or negative. And then so we can say the velocity of B is also equal to the velocity of D. What happened to C? Oh, I know what happened to C. They don't like to use C because they like to use it for the ICR. Makes sense, right? Sorry. Plus omega BD times K crossed with R. That thing's really long, isn't it? B with respect to D. So we're going to start out with 120J plus unknown omega BD. I should probably maybe right over to the side, the B with respect to D. So that's looking upwards and to the right, so they're both positive. In the X direction is going to be 24I, and then in the Y direction is going to be 10J. So I'm going to go ahead and distribute these, like having written all these out and done this enough times, that should go like this. So you could go 24, except write 24 instead of write 20. 24K crossed with I plus omega BD. And I'm going to go 10K crossed with J. We know that's J. We know this is negative I. So we're going to have negative 10 omega BD I. Boy, that's hard to read, sorry. Should say -10. Plus parentheses 120 plus 24 omega BD J. So we could combine this and that together and say, I guess which is going to be the easiest one to do is the J direction. Yeah, J direction, we could find the answer, right? So this is going to be, for the J, we'll have 0 is equal to 120 plus 24 omega BD. So omega BD is going to be a negative 120 divided by 24, which appears to be 5. Anybody agree with that? And then so we could go in the I direction and say that we have 8 omega AB is equal to -10 omega BD, which is a -5. And we get omega AB is going to be a positive 50 divided by 8, which is 6.25 radians per second. Switch over to acceleration here and say, couple things. Well, we could, okay. Well, we'll just march through. The acceleration of D is equal to the acceleration of E plus alpha dE K crossed with R D with respect to E minus omega dE. Did I say dE? Oh yeah, we have that. Okay, squared R D with respect to E. But that's stationary. This was a constant speed. So all we're really left with the acceleration of D is going to be negative omega, which is 20, times our R and D with respect to E, which is -6 I. So we get a 120 I inches per second squared.
Should the AU?
Yep, squared. Sorry. Go ahead, Sam, I'm sorry.
No, that's what I was gonna say.
Yeah. I screwed up, so that comes up to 2,400. So, but you know, you look at the thing and you can say, oh yeah, it must be going that way. And now we have to decide about BD and AB. I think it might be easy. You could do either one, and then you're gonna have to stop because we have two things we don't know. We don't know the alpha of this, and we don't know the alpha of that, the angular acceleration. So either one you can start with. So I guess I started to go with BD first. So we get the acceleration of B. It's going to be equal to the acceleration of D plus the acceleration of, nope, we're in vector. So we're going to go alpha BD K crossed with R B with respect to D minus omega BD squared R B with respect to D. And so we already have this value that we just found, 2,400 I plus omega BD, we don't know what that is, but the RB with respect to D, we're looking upwards, it's 24. And we have K crossed with I and plus alpha BD, and now we're going to go up 10. So that's going to be K crossed with J. We're going to go minus omega BD squared. Omega BD was -5, but it doesn't matter that it's negative because we're squaring it. And that's times our 24. And that's the I. Then we have minus squared 10J. A lot of stuff to write down, keep track of, but with practice you get good at it, and not only that, you will learn to be able to like organize your thoughts and keep track of a complicated thing and be able to soldier through with past the adversity. Believe it or not, that's an important engineering trait, to be able to just put your head down and do it even though it isn't pleasant. We actually have a value right here. They cut a bunch of corners in the solution manual that I think that don't help us at all. So 25 times 24, 25 times 24 times, so this ends up being 600, but it's minus 600, so that's going to take this down to, so this, can't do it in my head, I should, so 1800, right? And we have to have both put, no, this is going to be the I, so it's going to be a negative 10 alpha BD. That's going to be I. Yeah, I think I got that right. And then plus, that's negative in this, okay, it's not going to cancel out, so it's going to be 25 times 10, so it's a negative 250. And then that's still positive, plus 24 alpha BD, J. All right, so now we go and we go to the next, we go to link AB. And we have the acceleration of B is equal to the acceleration of A, which is 0, plus alpha AB, K, crossed with R, B with respect to A, minus omega AB squared R, B with respect to A. Bless you. So alpha AB times RB with respect to A, that's going to be 8 inches. It's going to be negative 8 inches. And it's entirely in the J direction. Right with that? And then for this part, we're going to minus 6.25 squared. And then RB with respect to A is negative 8. And in the J direction. So we have -8 alpha AB I plus 6.25 squared times 8. There's negative, so that's good. And it ends up being 312.5 J. And now we just have to set these two things equal to each other. That guy and this guy. And it looks like the J direction is going to be the way to go first because we get one of our unknowns out of the way. So we have -250 plus 24 alpha BD is equal to 312.5. So alpha BD and we're going to add 312 and 250 together.
Dr. Dio?
Yep, what did you write?
Isn't K cross J negative I?
You're right. Thank you. I don't know. Remember what the what did I say the answer was going to be? Yeah, it's got the right answer. 23.44 radians per second squared. So I is going to be our 1800 minus 10 times our 23.44 that we just found is going to be equal to 8 positive 8 alpha AB. All right, so 10 times that. I can hope, I'm not feeling it, don't know. 195.7. Let's see. Yay! It's positive, that means they're both positive, so they're both counterclockwise. So where's the ICR on this one? Is it over here? Is it over here? Is it right here? Is it right here? Is it right here? It's right
The other
there.
one. I think it's the other one. Is it that one?
It's a tricky one, right? Is it tricky? But just anytime it's a 4-bar, just make the links where the links intersect, right? Just keep imagining that like this velocity is coming up that way, so you have to draw a line through it. This velocity is either to the left or the right, so the line through it has to pass through right there. So then you can see that this must be coming that way, right there. And so here is our omega BD, passing that way right there. And you notice he's going clockwise, so that makes sense that it was negative, right? That's the direction it was going. And we could have taken 20 times 6, right? 120, and then divided that by our 24 and that was gonna give our 5, right? So that's why that happened right there with our ICR. And then if we were gonna go to the 3 diagram method for this piece right here, we would add an acceleration only in this direction. That's the acceleration of D going that way. Here we would have known this acceleration right here. This is the acceleration of B in the Y direction is also equal to the acceleration of B with respect to A in the normal direction, which is the omega AB squared LAB, right? So the only thing we had to do for this is to kind of like find out what that had to be. So because we would know this one, we'd apply that to both these places right in here, and say the acceleration of D, because it's known, put this one on here, we'd have a line like here, we'd be able to find that value right here, assume this alpha BD, we'll put this is the acceleration of B with respect to D in the normal direction. This is the acceleration of B with respect to D in the tangential direction. This is omega BD squared LBD. This is alpha BD LBD. And in terms of the angles, this thing right here is up 10 over 24. So we're going to go 10 over 24 and atan. So 22, we'll call them beta. Let me see beta. Anybody ever taken a beta blocker? Anybody taken a beta blocker before? It's like a secret. You know what? College students, man, it like suppresses your adrenaline, so like you don't panic. It's like you gotta give a presentation, man. Go get somebody to get you a beta blocker. There's no side effects. I don't think you can get addicted to them either. It's just, I don't know. Maybe I'm giving bad advice here, but I tell you, before my dissertation defense, the psychiatrist gave us a beta blocker. Be like, no fear, confidence. They're even thinking that like people who play chess and that kind of thing, they're thinking that that's performance enhancing drug, like outlawing it, because it's people just. Anyway. What the hell were we doing? All right, this angle, this angle right here. I was thinking of betas. Sorry, I had my beta on my mind. I drew it like almost 45, so it's a terrible drawing. And that always makes life difficult when you draw the thing like it's 45 degrees. So I got to kind of like picture where the angle is, right? So this is the angle right here that we're looking at. That's what beta is supposed to be. It's only supposed to be 22 degrees. Yes.
I was just confused how the tangent one is tangent and the normal one is normal.
Because I am tired. Thank you. Yeah. You're right. When you're right, you're right. Omega BD squared LBD. Alpha BD LBD. And here's my beta. And if that's beta, then that has to be beta, right? And therefore, that has to be beta. And if that's beta, that has to be beta. You're okay with that logic? Yeah, try to pick them. I think so. the thing that really messes me up is that I used 45 looking thing here. Okay. So here we have the acceleration of B in the x direction. So we don't know this. We want to avoid this guy because we don't know him, but we do know this value up in here, right? That's going to, you know, presumably we already got our omega AB squared, omega AB, I should say, 6.25 squared, and the length of AB is 8. So 6.25 squared 8 times is 312.5. This thing's been pointing over here for a while. This is going to be a wonderful video. Captured forever. Me telling high school, college students to get beta blockers. That's great. Okay, so the equation we're writing for this is the acceleration of B is equal to the acceleration of D plus the acceleration of B with respect to D in the tangential plus acceleration of B with respect to D in the normal direction. And so as I said, the y direction might be the way to go first, because we know this value, it's going up, so that's going to be 312.5, and nothing happening right here. We're not sure about this one, bless you, but as drawn, we have alpha BD times LBD, which we never got, right? I never got the LBD. Figured right over here somewhere, LBD. LBD is equal to 10, so that's actually 124 squared plus square root. So is it, that can't be right, 26? I guess, oh yeah, 5, 12, 13, right? So it's a 26. I always forget about that one, the 5, 12, 13 triangle. That means we could have done like the ratios of these instead of using the angles. That's probably why they have it that way. So you don't have to find the angle. So what did I say, 26? And we gotta only use the cosine of beta for that one. Cosine of 22.62. And then lastly, you have to go negative our BD squared. BD is 5. And the length, as we said, is 26. And we're going to use the sine because it's opposite from that beta. This is going down there, that's this that guy. So we have the sine of 22.62. So we could find beta BD. All right, so there you go. This is where that is right there, right? So that's going to be, that's the same equation as this one right here. That's the 312.5. This is going to turn out to be 24. And this right here is probably going to be negative 250. And we'll get the same thing. So if you go 25 times 26 times 22.62, sine of 22.62. Yes, get 250, and you could add them together and divide by 24, and we get the 23 point, yeah. So now if you go into the x direction, we can find out what AB is going to be equal to. And it's going to be AD, which we have somewhere. Where the hell AD go? I guess we never wrote it down, but AD was 2,400. Positive 2,400. Have a good weekend. And you too. So I have to go negative 23.44 and 26. And now take the sine 22.62. And then lastly, also in the negative direction, right? We'll take omega BD, or that's going to be the negative 5 squared, that's supposed to be a 5, times 26, times cosine 22.62. So you can find out the acceleration to be. So 2,400. Actually, I can flop that around. Take that times 26, 22.62. Sine times, and we're subtracting that out. Okay. And we're also subtracting 25 times 26. And the cosine of 22.62. And we're also subtracting that, which is like close to 600. Boom. So we get 1,566 inches per second squared. And then if we want to get the angular velocity, angular acceleration of this guy right here, we just have to divide that by 8. And we do, we get 195.7. So, demonstrated the other way. I asked the class last night this. Anybody ever, like, when you get done with something, just to be kind of a jerk, just go QED. Do you ever go QED? You sound all smart and fancy pants if you go QED at the end. It's a Latin phrase. Don't ask me what it stands for. I don't remember. It's Coro. And so what it means, and so it is demonstrated. So like you'll see at the end of some things when they're like a proof, they go QED. But if you just want to sound like smarty pants, when you get done at the end of something, go QED. You don't believe me, do you? I don't believe that that would be a funny thing to say in certain only if other people understand it. But if they don't understand it, they'd be like, "What the hell is that?" And then you can explain it to them. You can sound all smarty pants. You don't care. That's okay. My dynamics teacher, Don Paquette, would say all the time. He would look at us, look at the blank faces with sort of anger underneath, barely controlled rage at the annoying dynamics lesson that was given. And he'd be telling a joke, and no one would be laughing. And he'd be like, "Oh, you don't care." Okay. And he wouldn't laugh, but I would laugh. I'd laugh every time. I thought it was hilarious. Now I'm the only one. All right. I think that's enough dynamics for one afternoon. I feel as though there's a lot of learning that took place here. Be ready for this, right? Ready for this exam. Practice, 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 practice.
Do you think that's like the approximate like level of difficulty besides like?
I think this is too, I think this, I don't know if it's hard to judge for me until I've timed it out and tried to simulate what I think would be a standard pace. And I think this one's a little long. I mean, if I only gave 2 problems, it would probably, but like, the problem with giving 2 problems is some people just won't even be able to get started, they'll just be stuck. And then, so they'll start with a 50, you know, because they wouldn't want to have written anything down. I tell you, it happens, like a lot. No matter what I try, people leave problems blank. But the thing also, the other thing, telling you straight out, I think all of you, my students, right? Ask a frickin' question during an exam. If you're stuck, don't sit there and suffer. Tell anybody that'll listen, don't sit there and suffer. Come ask. It's not suck up. It's not a suck up rule. It's just like you're stuck. But maybe you do know the thing. Maybe you just need a nudge. But if you don't know what the hell you're doing, nothing you ask is probably going to really help you. But don't just sit there and suffer. Come ask questions.